this video is going to be the last one in the section of trigonometry, and I hope you found all of the videos helpful. We have spent quite a bit of time going through all of these things and putting together what I call the trigonometry toolkit. And so this video is going to focus on specifically solving trig equations, and it's just so important to keep an eye out for this. Is there a special angle somewhere? Is there somewhere I can use one of these fundamental identities? And very often at grade 12 level, is there a compound or a double angle hiding in this equation that I can use to solve? So let's take a look initially just at the foundations of trig equations. So what did we learn last year? This question says, determine the general solution of cos 3 theta plus 0,5 equals 0. So we know that this is a trig equation because we've got some trigonometry and it equals to something. It's not an identity because the question here is not saying show or prove, it's saying specifically determine. And then here they are referring to what is known as the general solution. So with all trig equations, we start off by finding a general solution, and then sometimes if they give us a domain, we can work and branch off and find a more specific solution. Okay, but the question will specifically say that. So for now, they just want the general solution, and that's a good place to start. So if you are asked to determine the general solution of something, the first thing you need to do is isolate the trig ratio. Okay, and what I mean by that is this 0,5 here, we can move over, and then we'll be left with cos on its own. So cos 3 theta is equal to, that's going to be negative 0,5. Okay, the next thing we do is we get a reference angle. Okay, and in beyond that is that we ignore the sign. So we're just going to use the 0,5 and we're going to get a reference angle. This sign is actually going to help us later to choose the quadrants. Okay, so we are going to use the sign, but we don't use the sign in obtaining a reference angle. Okay, so reference angle, we remember when we're looking for an angle, we use the arc cos function, so shift cos of 0,5. Now you may even recognize that as one of the special angles there, but basically we've got a reference angle now of 60 degrees. Okay, and now we're going to go back and we're going to use that sign and we're going to apply it to the cast rule. So now I ask myself, where is cos negative in this Cartesian plane? Okay, and cos is negative either in quadrant 2 or in quadrant 3, and so that's where I'm going to apply the reference angle. So in quadrant 2, I can then say 3 theta, that's what we're solving for if you go and have a look at the original question. 3 theta is equal to 180 degrees minus my reference angle there of 60 degrees. And then remember from grade 11, general solution, we always added 360k, and we needed to specify that k had to be an integer. Okay, so no commas or fractions or any weird things like that. We want to add full revolutions or full periods. It's not necessarily a revolution because remember, the sine and cos graph, we add 360k, so sine and cos plus 360k because that's the period of a sine and a cos graph, and then tan has a period only of 180, so plus 180k there. Okay, remember that. So that's going to be applying there to quadrant 2, and then the other quadrant that we said we would work in is quadrant 3. In quadrant 3, we say 3 theta is equal to, and this is a 180 plus quadrant, so 180 plus 60 plus 360 degrees k. K is an element of the integers. Okay, so you can either semicolon and state or put that in brackets, but very important, you could cost yourself a mark if you forget to mention that. Okay, you only need to say it in the first step of applying these quadrants, and then you're good. So now we've got 3 theta is equal to 180 minus 60, that's 120, plus 360 degrees k. And then let's divide everything by 3. And finally, we will have solved this. So theta is equal to 40 degrees plus 120k. That's one part of our general solution. Okay, on this side, 3 theta is equal to 180 plus 60, that's 240. And then we're going to do the same thing. We want to divide everything by 3. And we end up then with theta is equal to 80 plus 120k. So that's how the general solution works. Isolate the trig ratio, get a reference angle, allocate the reference angle. Okay, they don't stay this straightforward though. Sometimes we have to do some factorizing first, etc. And like I said earlier, we're probably going to have to refer to our double and compound angles. So let's look at 2 more examples. Determine the general solution of cos alpha cos 27 plus sine alpha sine 27 equals 0,75. Okay, so step 1, we want to isolate the trig ratio, but there's really a lot going on here. And so what we need to be on the lookout for, because this is a grade 12 trig equation, is this something that I've recognized before? It definitely looks like something that I see on my formula sheet, one of these compound angles. So we want cos cos, sine sine, with a plus in the middle, and so that can actually simplify to cos of A minus B. So now let's take a look at what this whole complex looking equation will become. Instead of cos cos sine sine, we can write it as cos and then alpha minus 27. So that's going to become nice and neat. Cos alpha minus 27 degrees is equal to 0,75. Okay, so that's the first thing we do. Now the trig ratio is isolated. So actually it looked complex, but it was quite a straightforward question. So next up we want to get a reference angle. And remember, we don't want to use any sign, but in this case it's a positive 0,75. So that doesn't matter too much. We can say shift cos and then 0,75. And that gives us a reference angle there of 41,40962211. Okay, why am I keeping everything? Because this is not my final answer. Okay, so you can use the memory functions on your calculator to keep that reference angle, or you can write all of the decimal places. But important at grade 12 level, we definitely don't want to be rounding off too soon. Okay, now we need to apply this to some quadrants. So where is cos positive? It's positive in quadrant 1 and in quadrant 4. So now I can apply that reference angle there. In quadrant 1, the angle alpha minus 27 degrees is equal to just the reference angle plus 360 degrees k, and k is an element of the integers. In quadrant 4, our angle there, alpha minus 27 degrees, is equal to 360 minus my reference angle, 41,409 dot dot dot, plus 360k, k is an element of the integers. Okay, now we can simplify. This 27 can move over. And that's going to happen on both sides. So our first solution there is going to be alpha is equal to, now I'm allowed to round off. This is my final answer here. So 68,41 degrees plus 360k. And on the other side, we want to say 360 minus and then plus that 27. So typing that all into my calculator, I end up there with alpha is equal to 345,59 degrees plus 360k. Okay, so there we have another relatively straightforward trig equation. Again, we isolate the trig ratio, get a reference angle, and apply it to the quadrants. Okay, let's see if we can get one more example that can get us thinking. Solve for beta if 1 plus sine 2 beta, double angle, instantly see that, minus 4 sine squared beta is equal to 0, and beta is an element of, and then they give us a domain. So this is, first of all, we're going to do a general solution here, and then we're going to apply that and come up with a very specific answer that fits within that domain. Okay. The first thing I noticed here is that we're dealing with a double angle, so let's have a look at those double angle formulae. So we can rewrite this left-hand side here as 1 plus, and then instead of sine 2 beta, we can write 2 sine beta cos beta, and then minus 4 sine squared beta, and that is equal to 0. Okay, now we're going to need to isolate the trig ratio, which doesn't seem possible at this point in time. So if ever you hit something like that, then remember your options are always to factorize, because especially the fact that there's this square here hiding in this equation helps me to realize I'm probably going to have more than one answer here. Alright, now there's a slight problem here because we've got a 1 and then this middle term has got a sine and a cos, and then this other term here just has sine squared. So the fact that we have a sine and a cos here makes me think, let's change this 1. We know that fundamental identity, so we can rewrite that as sine squared beta plus cos squared beta, and then plus 2 sine beta cos beta minus 4 sine squared beta. Okay, and then we can collect some like terms because there's a sine beta and there's a sine beta. So we'll be left with, it's going to be cos squared beta plus 2 sine beta cos beta minus 3 sine squared beta. Okay, and now I need to try and factorize this. Okay, if it stresses you out, you can use the K method, but you do know how to factorize this. Okay, we know we're going to have 2 brackets, so we're going to really start there. Because the coefficient of that first term is 1, it really does help us because they'll each just get a cos beta. Okay, cos beta times cos beta gives us this first term here. Then I need factors of 3 that can help me end up with a 2. Okay, so the factors of 3 are simply 3 times 1. Okay, so I can then use those, and remember that that's just the coefficient of a sine. So we're going to say this one's going to be a 3 sine beta, and this one is going to be a sine beta, or 1 sine beta. Okay, and then I want to end up with a positive middle term. So it's going to have to be plus 3 sine beta minus sine beta there. Okay, and so now I can dive into 2 separate equations here. This is a great example of what we can expect. So now we can say, well, either cos beta plus 3 sine beta is equal to 0, or cos beta minus sine beta is equal to 0. Okay, and we are going to solve. Let's start with this first one. Let's take the 3 sine beta across. So cos beta is equal to minus 3 sine beta. And then if you remember from last year, what we like to do if you're sitting with a cos and a sine is that you can actually divide both sides by a cos. Okay, why do we like to do that? Because sine over cos becomes tan. Okay, so what I've just done now by doing that is cos beta over cos beta is 1 equals minus 3 tan beta, which is definitely doable. Now we can divide both sides here by minus 3. Okay, and so we end up there with the fact that tan beta is equal to minus 1 over 3. Okay, and then we get a reference angle there, and we're going to apply it. We are going to run out of space. We're going to have to make some plans here, but let's hold on that now, and let's finish the other option. Okay, you can really do this in any order that you want, but let's take this cos beta minus sine beta. So cos beta, let's take the sine beta over, equals sine beta, and we're going to do the exact same thing where we divide both sides by cos beta. Okay, and that gives us then tan beta is equal to 1. Okay, so be careful now. We've got so many solutions coming our way. We are ready, though, to get a reference angle in each case. Remember to ignore the sign, reference angle. So we're going to, on the calculator, shift tan of 1 over 3. Okay, and there we get that reference angle. Or our other reference angle, that's a special angle straight away. So if I said shift tan, I can tell you now I'm going to get an answer there of 45 degrees. Okay, so I've got my two reference angles, and now I need to think about applying the cast rule. Right, where is tan negative? Okay, tan is negative in this quadrant here. Okay, tan is also negative down here, but remember, because tan has a period of 180 degrees, whatever happens in quadrant 1 and 2 is going to repeat in quadrant 3 and 4. So I always tell my students, if you're going to forget that it sometimes applies and sometimes doesn't, then do all of the quadrants. But it's so helpful to remember that you can actually just work in the first two quadrants when you are dealing with a tan ratio. Okay, so now we can say, well, then our angle, which is beta, is equal to, in the second quadrant, it's 180 degrees minus this reference angle plus 180k, and k is an element of the integers. Why plus 180k? Because we are dealing with a tan ratio there. Okay, so that gives us 161,57, and then let's go to our other solution here. Where is tan positive? That's in quadrant 1. Okay, all the ratios are positive in quadrant 1. And seeing as though we're just applying to the first two, that's what we want to do. So here, beta is equal to 45 plus 180 degrees times k. K is an element of the integers. Okay, so now what we're sitting with is two general solutions. Let's put that beta there. Okay. And we want to apply these general solutions now to get a specific solution in this domain that they've given us here. And so what you need to do is you need to then substitute in values for k. Okay, I always tell my students, start and work out. What is it if k is equal to 0? Get an answer. If k is equal to minus 1, if k is equal to 1, etc. Okay, I'm going to work out those answers quickly, and then we're going to come back and discuss. So in each instance, I have taken a value for k and I've substituted in it, and then just worked it out. So 161,57 plus 180 times 0 gives me that. Plus 180 times minus 1 gives me that, etc. And I've done the same here for each of them. And what we're supposed to be doing while we're working them out is deciding, do they fit into this domain or not? So 161,57, that is going to be a solution. It does fit. Okay, minus 18,43, that is going to be a solution. It does fit. 341, that's too big. So that one we don't want. Okay, and generally what I tell my students to do is keep going until you hit something that doesn't fit. So you could then try and substitute in a minus 2. I just quickly did it mentally and realized that's also going to end up being then too small. So we've just got two solutions there that apply. And then on this side here, to our other solution, 45 degrees does fit. So let's give that a tick. Minus 135 is too big, too small. That's much smaller than minus 90, and 225 is also too small. So there we've got three solutions that fit, and so we can now write down our answer. So therefore, beta is an element of, and then we're going to list from smallest to biggest. So minus 18,43 degrees, 45 degrees, and 161,57 degrees. So there you have it. We used our double angles. We then factorized. We got a whole load of things to work out. Got our reference angles, applied to quadrants. And once we had the general solution, we then took that and substituted in values for k to end up with a specific solution.